Okay, we're going to start so that we'll have plenty of time for those people who are going to do the makeup after the lecture. So we'll do our lecture first and then stop, and then if you're sticking around for the makeup, you stick around for the makeup. So we'll be able to finish that in time. Okay. And next week is spring break, so I think you just have one homework to work on. Wow, how did that happen? Just one homework to work on during spring break, okay? And then we'll resume, hopefully, unless we're all quarantined. I'll see y'all on the 16th, right? So there's the one homework that you'll be working on over spring break. Those are volume problems. In a sense, those are a few of them can be challenging. They all involve integration, so of course that's by itself is definite integration too. So in itself, that's challenging just because it has lots of calculations in it, possibly. But conceptually, most of the problems are really straightforward because we have a nice formula that we got to just at the end of class last time. So we're going to practice that formula again. That makes the setting up the problem pretty straightforward. Then executing the definite integration might be another issue, okay? But at least you'll be able to set up the problem for these. There's not that many. I think there's 9 problems on there. But now remember the DE homework, right? You're going to finish this evening, right? That is due this evening, okay? So then you've got plenty of time to focus on that volume homework. Okay, over the spring break. All right. So we may get to look at one or two of those volume homework problems before we finish today. Before we finish the lecture today, but I want to go back and do examples from the notes first. Okay. All right. So remember last time we were learning how to use definite integration, right? The process of definite integration to compute the volume of a solid. Now, these solids, these are three-dimensional solids, but they're all formed in a similar way. They're formed by taking a region beneath a curve down usually to the x-axis, but not always to the x-axis, but a region beneath a curve or between two curves possibly, and then rotating that area totally around the x-axis, 360 degrees around the x-axis, and that will sweep out a volume. Or you can also think of it as it will form a three-dimensional object that has a volume. And then we're trying to compute the volume of that object, right? And so we learned last time how to apply the process of definite integration to compute that volume. And applying that process of definite integration leads to this formula, okay? So you really don't have to rethink the definite integration, process that we applied, in the way that we applied it last time, in a very step-by-step fashion. You don't have to do that every time, right? Because you can condense all of that into this nice formula, right? Okay. So this formula says exactly what I just mentioned. If you have a region beneath a curve down to the x-axis, but between two boundary values on the x-axis, x equals a and x equals b, right? And then if you take that region and rotate it around the x-axis, again, that sweeps out a volume, and there is the formula for the volume of that object, right? Okay, so notice it involves pi. That comes from the fact, remember, that you're moving this, you're rotating this region in a circular fashion, right? 360 degrees around the x-axis. So circles are involved in a sense, right? You're sweeping that region out in a circular way, right, around the x-axis. So that's sort of where the pi comes from. In a very loose manner, and then times the definite integral from a to b. Those are your boundary values on the x-axis, and then you have this function squared, and that function is the function that gives you the radius of the object at any point along the x-axis. But typically, that is going to be the formula for the curve that you're rotating around the x-axis. All right, so that curve will. Have this curve, right, will have a formula, right? And So usually the formula for that curve is what is going to go here, but not always. So there are some variations on this formula, okay? But that's the basic way the formula works. Notice that you're squaring that though, okay? So the square is part of the formula, right? And that's it, okay? So if you can evaluate that definite integral right, then you can compute the volume. Of course, easier said than done, right? Evaluating definite integrals can be difficult, especially depending on how complicated this radius function is, right? Okay, so if that's a complicated function, notice you're squaring it too, right? So it makes it that much worse. That can be a hard definite integral to evaluate. In fact, sometimes we are going to, in at least a couple of problems, we're going to rely on having the computer help us evaluate that definite integral. So we're not going to try to do it by hand. We'll have the computer compute the definite integral for us, all right? Of course, in that case, we'll only get sometimes we'll only get a decimal approximation for the volume, but depending on the homework problem, that might be enough, right? Okay, so let's actually apply this now. That's enough of me just yammering there. So let's find the volume formed by rotating the region between this curve now, 1 minus x squared. So that's going to be a parabola of some sort around the x-axis. So see, it's just the very standard setup, right? So we have an area beneath this curve down to the x-axis. Our boundary values on the x-axis are very simple here from 0 to 1. That's nice, so that'll probably make the calculations easier at some point in the problem, right? And we want to take that region and rotate it around the x-axis. I drew a picture of this situation, and I'll show you how you can draw these pictures in a moment here. All right. So really, here is I've got a lot of extra writing here, but here is so there is that region. Okay. That curve, 1 minus x squared, is this curve, which is the top boundary for the region, right? Okay. And so the region is this green area beneath that curve down to the x-axis, starting at x equals 0 and going to x equals 1. So we're going to take that region and we're going to rotate that 360 degrees around the x-axis. When you do that, if you can sort of ignore my drawing on this picture, you get this shape, right? Okay. Let me erase some of this. Remember that what I had drawn in there was just to remind us, right, that the way we actually compute that volume, right, is by cutting that volume into cylinders, right, and then adding up the volumes of each of the cylinders, and then thinking about what happens as the number of cylinders approaches infinity, right? Take the limit of the volumes of those cylinders as the number of cylinders approaches infinity. That's where the definite integral formula comes from, okay? But if we erase that, all those cylinders, there's the picture of that volume, okay? It was just this area, right, rotated around the x-axis. So you get this, what is that, kind of a tip of a missile, right, is what that looks like, okay? And so if we're thinking kind of violently, you might think of a nicer image for that, all right? So anyway, that's what we're trying to compute the volume of. It's not going to be a very big volume, right, because you're only going here from 0 to 1 on the x-axis, and notice the radius, right, of not the diameter, but the radius of this object, right, from the x-axis up to the surface of the object. That's not ever very a long radius, right? It looks like it doesn't go above 1 on the y-axis. So this is not a very big object, right? It's a small object, so it shouldn't have a really big volume. All right, so let's see if we can calculate that. All right, so we just have to use our formula, right? So what does our formula say that that this volume is going to be? So let's recall that, right? There it is. So what do we do now? V here is volume. So we take what? Y'all going to have to talk to me here, okay? Or we're going to have time to take the makeup test. What? So what? Pi, right? Okay, and then what? Yeah, this is definite integral, right? Okay, from where to where here? 0 to 1, right, yeah, we're going from 0 to 1 on the x-axis right here, from 0 to 1. And then what you want to square is the function that gives you the radius of that object, right, at any point along the x-axis. The radius of that object is going to be this, right, okay, at any point on the x-axis. Well, of course, how do you get the radius of that object? What is that related to? What? Radius and diameter are indeed related, right? Okay, but in this particular instance, how would you get that length? Okay, you're going from the x-axis up to what? Up to this curve, right? Okay, so how do you find that a distance between the x-axis and that curve? That height right there. Plug it into what? Plug what into what? Into the equation for what?
The region between.
We don't have an equation for the region, but what do we have an equation for? 1 minus x squared, right. That's that blue curve, right, okay? So you plug x into the formula for the blue curve, right, okay, which was 1 minus x squared, right, okay? So that's what I was mentioning earlier, right? The formula for the curve that you're using to form the object, right, that is usually the radius of the object. Not always, but most of the time that's just the radius of the object. So this, in other words, this length is f of x. And remember, f of x in this particular instance is 1 minus x squared, right? Okay, so that's what this radius is. So we're going to put in here 1 minus x squared. That's all there is to it, right? And then you're going to square that. Don't forget the square, though, okay? Otherwise, it's going to come out completely wrong, and that's it. So if you can evaluate that definite integral and then multiply by pi, you're done, okay? So, well, let's see if we can do that. So, here's what I'm going to do. Let's go off to the side here, right? To evaluate this definite integral, right, I need to find the antiderivative of 1 minus x squared, right? Okay, so rather than doing that all simultaneously, let's go up here and let's see if we can calculate the antiderivative of 1 minus x squared squared, right? And I'll do that by squaring out the 1 minus x squared. So that's going to give me 1, and then I think minus 2x squared, and then plus x to the 4th. So if you don't trust me on that, just do that, a little bit of algebra. Take the 1 minus x squared and then square it, and you end up with 1 minus 2x squared plus x to the 4th power. All right, so we want the antiderivative of that. How do we compute the antiderivative of 1 plus 1 minus 2x squared plus x to the 4th power? What rule can we apply here? Oh, we are saying several things at once, but I wasn't sure I heard what I was looking for. What? Anti-power rule, right? Yeah, you would just use the anti-power rule, right? 3 separate times. You would go term by term. So you would calculate the antiderivative of 1. You can do that using the anti-power rule. You calculate the antiderivative of minus 2x squared. Do that using the anti-power rule, and calculate the derivative of x to the 4th, again using the anti-power rule. What's the antiderivative of 1, of course? X, right, okay? You really are using the anti-power rule there, but usually don't have to think of it like that. So you get x, and then what about here? This is what? Minus 2x what? Cubed over 3, right? And then this is x to the 5th over 5, right? So you get, well, not the prettiest antiderivative in the world, but that's it, right? Okay, at least we got it. Remember, you don't need the c here because we're going to use this in a definite integral. So let's plug that in. So we have x minus 2x cubed over 3 plus x to the 5th over 5, and we're evaluating this from what, 0 to 1? Is that it? Yeah, nice, okay. So glad it's 0 to 1, right? So let's see, when you plug 1 in there, you're going to get what? 1 minus, is that 2/3? And then plus 1/5, right? And when you plug 0 in there, of course, what happens? You just get 0, so you can drop that. So you just have a pi times 1 minus 2/3 plus 1/5. So if we can do a little bit of fraction arithmetic there, right? We've got it. Let's see. So 1 minus 2/3 is 1/3, right? 1/3 plus 1/5. I think we're going to have to convert that to 15ths, but 1/3 plus 1/5, I think, is 8/15ths. So if you don't trust me, just try doing that, okay? So I think I have pi times 8/15ths, which is, well, that's pi times 8/15ths, right? That's 8 pi over 15, okay? So there it is. That's a volume now, though, remember. So the unit of measure is cubic units. I don't know if those are inches or feet or miles. Okay, it doesn't really matter. It's cubic units, right? Remember, this is a volume. That's not that big, right? That's about 1/2 a pi, which is 8/15ths is about 1/2, not quite, but about 1/2, right? Times pi. Pi is 3.14, so you know you get maybe about 1.5 or something like that as the volume here. That sounds reasonable. We knew the volume wasn't going to be very big, right? Okay, so. At its easiest, that's the way the process works. All right, so in the homework, you're going to have lots of examples very similar to this one, okay? The first few problems are all going to look like this, okay? Now, but let me show you not so trivial examples. This one's not too bad, but a little bit harder. Okay, so we want to find the volume of, the solid formed by rotating the region between y equals square root of x and y equals x squared. Well, those are kind of inverse functions, right? Because square root of x and x squared, those are inverse operations, right? So, so we want the region between those two functions. And we're going to rotate that around the x-axis. So notice this region is not quite as simple as in the prior example. You don't have just the area beneath the curve down to the x-axis. You have the area between two curves, right? So if you draw a picture of that area, it's going to be the area here between these two curves. So if I shade that area in, there's what it looks like, and then we're going to take that and rotate it around the. We're going to take that and rotate it around the x-axis. So when you do that, what sort of thing do you get? What does that object look like? Can y'all visualize that? So you take this and rotate it around the x-axis. So notice it's going to be hollow in the middle because this part will be empty, right? Okay, you're just taking this and just this and rotating it 100 degrees around the x-axis. I want to point out this is solid, though. Okay, right, okay. It's going to be a solid object, but it's going to be kind of hollow in the middle, so you could, this part's going to be hollow, so you could pour water in it, right, and it could hold water, for instance. So how would you, what? Kind of like a funnel, right? Yeah, a little bit like a funnel, but it's a funnel that has some thickness to it, right? Okay, yeah, okay, because the sides of the funnel are going to be like this thick, right? Okay. You can also think of it as kind of a flower shape when you rotate that around the x-axis. Here's actually the picture of it. So look like this, all right? Now you have to kind of squint a little bit and imagine it a little bit. This picture isn't perfect either. But remember, the middle of it here is hollow, you see, okay? So this part is really empty, and it's only this part right there that's solid, okay? So I was thinking if we turned it up like this, where it's upright, it kind of looks like a flower, right, okay? Hollow in the middle, but also like a funnel, okay? Well, there it is, okay? So at least we know what we're working with, right? And so now we want to find the volume of that, not the volume of the inside, okay? This volume. So the volume of the object itself. So if we were going to construct it, if we were going to construct this object with glass or plastic or something, how much glass or plastic would we need to create that that object. All right. So so that doesn't quite fit into our formula, right? Because our formula says we just want formula works just if you're beneath a curve down to the x-axis, right? But in this case, we are farming an area beneath a curve, right? Beneath this curve, which is square root of x, but we're not going all the way down to the x-axis. All right, because we're stopping at this red curve, which is x squared. Okay. All right. So how can we think about this? So we have to be a little bit indirect. Any suggestions there? I mean, what would the formula allow us to compute? So if we were just relying on the formula, what could we actually calculate from that formula? The volume of what, though? But which solid now? Not this solid, okay? But which solid could we calculate a volume of here in this picture? Yeah, so yeah, you're getting to it, okay? But I'm trying to lead us to see why what you're getting ready to suggest actually works. All right. So again, with the formula, you can find the volume when you again rotate a region around the x-axis, but the region has to be between a curve and what? The x-axis, right? Okay. Right. So we do have a couple of curves here, though, correct? Right. So using the formula, right, we could find the volume of the object if we rotated the region, for instance, below square root of x all the way around the x-axis. So what would that region be? The whole region below square root of x, not stopping at that red curve, right, but going all the way down to the x-axis. Let's draw a picture of that. So what would that whole thing be? Well, below square root of x here, right, all the way down to the x-axis, right? So that would be all of this, right? Okay, and we could rotate that region and calculate its volume just using the formula. All right, so let's write down the calculation for that. Let's write down the definite integral for that. So if I were going to take all of this, this is too much, right? But if I were going to take all of this, right, and rotate it around the x-axis and calculate the volume of that thing, right, how would I do that? Let's call that big volume, right, because that volume is bigger than we want, right? So I'm going to call this big volume. So what's the formula for the big volume? Let's see, it's going to be a pi, right, because they always start with pi. And then what are the limits of integration here? Yeah, along the x-axis, you're just going from 0 to 1, correct? Right? You're just going from 0 to 1. And what's my radius function now? So what's the formula that gives you the radius of this object? Radius is the distance from the x-axis up to the edge of that object. So going from the x-axis up to the edge of this object, that's the radius. What's that distance? All right, let me where did I put that x? Was it here or was it there? All right, so I'm not going to be able to change color. It's going to be hard to see here. Let me try to draw it kind of thick there. All right. So what I want to know is what is that length right there? Okay. But I have to be that length has to apply for any x that I choose, right? Okay. So the x could be here, or the x could be here, or the x could be here. So you can't say that is 0.6. All right. Okay. Because the x is a variable, right? Which one? Which one? What's this one? Square root of x, right? Yeah, that length is square root of x, right? Okay, right? Because that is from x up to this curve. That distance is square root of x, right? Okay. All right. So our radius function here is square root of x. And what do we do with the radius function? This is nice, aren't we lucky? Because what are we going to do with that? Square it, right. So I get square root of x squared. How nice, okay? So there is the big volume, right? That's too much, though, right? Okay? Because I took this whole region, right? And I rotated around the x-axis. So you get this big solid object, right? Too big. Now, but there's another volume that we can compute, right? Okay? Because we have two curves in the picture. So what's the second volume I can compute here? What? The volume, that you would get by what? Taking this area, right? Okay? Taking this area and rotating it around the x-axis. I'm talking about the area beneath the red curve, right? Okay? The area beneath the red curve. I don't know if I can highlight that area. Let me try putting some more squiggles in here. So I'm talking about this region, the region beneath the red curve, right? Down to the x-axis, this region, okay? So that, if you wrote, by the way, what does that look like when you take just this region and rotate around the x-axis? How would you describe that? That's kind of a trumpet shape, right? Okay? When you rotate that, you get this, can't bend my hands like that. Probably somebody can, right? Okay? But anyway, you get like this, right? Okay? But remember, that's a solid object, though, because we're rotating this all the way around the x-axis. So that volume is also, we can also compute that, right? That's a smaller volume, right? Okay, correct, because that's just going to be a smaller volume, right? So let's call that the small volume. So what's the integral for that? So you have what? Pi, what are the limits of integration? 0 to 1 again, right? Except, what is your radius function here? X, what is it? Oh, x squared, right, okay. And what do we do with that? Square it, right, okay. All right, so now we've got that smaller volume. Now, how can I take those two volumes and get the volume I was really interested in, which was just this piece rotated around the x-axis, right? Okay? I just wanted the area between the two curves rotated around the x-axis. So how can I derive that from these two volumes that I've already computed? You said it. What? You just take the big volume minus the small volume, right? Okay? You take the large object, right? This entire area rotated around the x-axis, and then you just cut out the middle, right? You cut out the middle. That's this small area rotated around the x-axis. And what you're going to get left with is exactly this picture, right? Okay? The volume that you'll be left with is exactly this picture, right? This part rotated around the x-axis with the middle part cut out, you see, okay, when you subtract off the smaller volume. So we have to do, it looks like we have to do two calculations here, but let's see how this looks when we write it down. So I'm going to take big volume, right, big volume there, minus small volume, just as we said, right, and that's going to be this integral, so pi integral 0 to 1 square root of x squared, and then minus pi integral 0 to 1 x squared squared, right? Oops, I got to put a dx here. Don't want to forget that. But look, those two integrals have the same limits of integration, right? Okay, so I can combine them into one integral, and I can factor the pi out in front, because they both have that factor of pi in front of them, right? So I can rewrite this, I'm not sure if it's helpful, but I can rewrite this as pi, then integral 0 to 1 of, well, what is square root of x squared? That's x, and what's x squared squared, of course? That's just x to the 4th power, right? So you can put those in one integral, and now you can compute this. That looks a lot easier, right? Okay. All right. Now let's. All right. So let's see what this is. So we need to find the antiderivative, right? Y'all can write down that antiderivative just so fast. So what is the antiderivative of x minus x to the fourth power? How do you find the antiderivative? What rule there? The anti-power rule. So what's the antiderivative of x? X squared over 2, right? And what's the antiderivative of x to the fourth power? X to the fifth over 5, right? Ah, great. So I have pi here times, and it's x to the x squared over 2 minus x to the fifth over 5. And we're going to evaluate that from 0 to 1. How nice. Nice limits of integration here, right? So I have pi times, well, when you plug 1 in there, it looks like you get what? 1/2, right? 1 squared over 2 is 1/2. And then minus 1/5, right? 1 to the fifth power over 5 is 1/5. And when you plug 0 in there, yeah, you always love 0 as limit of integration, right? Because works out so nicely always. So when you plug 0 in there, it just disappears. So this is it, what you get. What is, good thing it came out positive. We didn't want it to come out negative, right? Okay, because these volumes should not be negative. Let's see, but what is 1/2 minus 1/5? 3/10? Yeah, okay. So check that arithmetic if you need to, but that is 3/10. So you end up with 3 pi over 10. Cubic, because this is a volume, so cubic units, not square units. Areas are square units. This is cubic units, right? Because we've computed the volume of that flour, okay? Neat. So if we wanted to construct that flour out of glass, for instance, we would need 3 pi over 10 cubic units of the glass, okay, to construct that object. All right. Now, another a question that we might ask, and well, we are going to ask it, is but not immediately, not today, not what is the volume of the object, but another thing we're interested in is what is the surface area of the object. So if we wanted to paint the object, how much paint would that require? Okay. Surface area is an area, though, so it is measured in square units, not cubic units, okay? Well, we're going to learn how to compute the surface area of this object shortly, all right? Okay. Well, I've got one more example. Okay, we've got time. You're not going to like this one, I'll just warn you, but it's not that bad, but it's a little bit confusing. All right, so now we want to find the volume formed by, again, we're rotating a region, right? Okay, and it's the region between this curve, 1 minus x, and y equals 0. Of course, y equals 0 is better known as what? Yeah, the curve y equals 0, it usually goes by another name. Not the origin. This is a curve. Origin is a point, right? Okay. But what curve is y equals 0? If you graph y equals 0, what do you get? You get a horizontal line. You get a very particular horizontal line, though. What horizontal line do you get? Okay, let's just do that. So there we go. There's our set of axes, and we graph y equals 0. So what line do I get? The x-axis, right? Okay, you're going to draw a line right over the x-axis. So this is really the region between 1 minus x and the x-axis again. It's just being asked in a different way, all right? So it's the same region. But so if we were rotating that around the x-axis, this would all be easy, right? Okay. But unfortunately, that's not what we're rotating around. We're rotating it around a different thing, okay? We're going to rotate it around y equals 2. So not the x-axis, but around the line y equals 2. So we do have to, this does require our spatial imagination a little bit. But here's a picture of the situation, okay? So there is 1 minus x. That's just a straight line, of course, right? And there's the area between the green shaded part, right? Is the area between the x-axis and 1 minus x, right? Okay, so all that's straightforward. So if we were just rotating this around the x-axis, we would just plug 1 minus x into that volume formula and square it, right? Okay, multiply it by pi, and then we'd be done, okay? By the way, what sort of thing do you get when you rotate this region around the x-axis? That's a regular shape, so it has a name. What? Cone, yeah, okay, so you get a cone. All right. We actually know how to compute volumes of cones from geometry. We have a formula for that in geometry. You can look that up. And so you really wouldn't even need calculus for this, because you can do this with just regular geometry formulas. All right. But what we cannot do with regular geometry formulas is what really asked for here, which is we want to take that region and rotate it around y equals 2. So there's y equals 2. Right, okay, there's the line y equals 2. Of course, that's just a horizontal line, right? And we're going to rotate this around y equals 2. Okay, so can you see what that thing is? Can you think of what that thing's going to look like when you rotate it around y equals 2? Take this and rotate it around y equals 2. Okay, so so think of this as coming out of the screen. We're rotating it around y equals 2, right? Okay, so when it hits the axis, when you rotate it around, it's going to hit the plane again, right, at some point. So what's the top part going to look like? The part that's when it touches the plane again on top. See, you're rotating this around y equals 2, so it's going to hit the plane again up there on top, and it's going to hit an area on top of y equals 2, right? What does that part look like? It's the same, except what? Just flipped, right? Okay, so if you draw that, I think it's going to look like this, right? Yeah, you just flip this area right around y equal 2, and you would get that up there. Okay, so this area is also part of your object, okay? But remember, your object is a three-dimensional object. It's not just these two pieces, okay? So it's a three-dimensional object. It's solid. It's not in two pieces. It's solid, okay? So what is it? On the outside, what does it look like? Really? Okay. A cylinder, that's right, okay? It's like a cylinder, correct, right? See, again, think of this. I'm rotating this around y equal 2, right? So this edge, think about this bottom edge here. It's going to get rotated, all the way around, right? Okay? So that bottom edge, by the way, this bottom edge is going to be the surface of the outside surface of the object. So it's going 360 degrees. So the outside of the object is going to be round. You've got a round object here, right? Okay, that's why you said it looks like a cylinder. You're exactly correct. But it's not a cylinder, because cylinders are solid. This thing is not solid. What's missing? The inside, right? Okay, this piece, right? All of this is hollow. Okay. All of that's hollow. So you have a hollow cylinder, right? Okay. We see cans are hollow cylinders, right? So we're used to looking at hollow cylinders. But what's different about this hollow cylinder is the sides have some thickness to them, right? Okay. The thickness of this area, right, is the thickness to the sides of this can. Okay. So you have this kind of unusual can shape, right? Okay. And we want to figure out what is that volume. All right. Now remember, the only thing we have to work from is that one volume formula. So we have to apply that, somehow, right? Okay, to answer this question. All right. So, all right. Here's how I'm going to think. I'm going to think of it exactly the way I did almost exactly the way I did previous problem. Look, suppose that you took this entire square, not just this piece, right, but this whole square, it's not a square, this whole rectangle, right? So suppose you took this whole rectangle below y equal 2 down to the x-axis and rotated that around y equals 2. So let me fill in the rest of that square, right? So suppose you added this area plus the green area. You added this area, right? And you rotated that whole rectangle around y equal 2. Then what would the picture look like? That would be a cylinder, right? That would be a solid cylinder, okay? You would get a completely solid cylinder. Well, let's see if we can calculate the volume of that completely solid cylinder. That's too big, right? Okay, because our cylinder has the middle taken out, but that's kind of partway there. All right. So again, let's call that big volume the whole cylinder. Now we can look up on Google and find how to compute the volume of a cylinder. Actually, I think we wrote it down. Didn't we write it down last time in the notes? Oh yeah, we did. Right. Okay. I was going to say we could look this up on Google, or we could use our we could try to use our integration formula, but I think we don't need the integration formula. We don't need Google either, because we mentioned last time, right, how to compute the volume of a cylinder. What was it? It was pi, right? Okay. So you start with pi, and then what? The radius squared, right? Times what? Did I call it the width? Yeah, the width, right? Okay. Well, so for this big cylinder, right, that you get by rotating that whole rectangle around y equal 2, well, you have pi still, right? But what's the radius? Well, what's that distance there? It's 2, right? Okay. The radius is 2, right? Okay. Remember, this is going to be the center of the cylinder, right? When you rotate around y equals 2, this line becomes the center of the cylinder. So the radius would be whatever this height is. It's 2. Notice it's always 2, right? Okay. Cylinder always has the same radius from left to right. Okay. So the radius is 2. So you get 2 squared. That's nice. Times then what's the width there? 1, right? Okay. This is what I was calling the width in the notes, and this is 1, right? Okay. Or you can think of it as height also, maybe. Okay, is 1. So there is the volume of this whole rectangle rotated around y equals 2. Okay. Now, how do I work backwards to what I want, right? Okay, because I only want this part rotated around y equals 2. So what do I have to cut out of the big volume? No, just describe it to me in words. What do I want to cut out of the big volume to get the volume that I'm interested in? Yeah, this part, right? Okay, the part in the middle. So somehow I have to calculate, if I take this, right? Okay, if I take this, just this area, and rotate it around y equals 2, right? What would that volume be? Okay, so if I just took this part, rotate around y equal 2, that's going to be a smaller volume, right? Okay. And if I cut that out of the big volume, in other words, if I take the middle out of this big cylinder, what will be left over is that piece that I wanted, right? Okay. All right, let's see then if we can figure out what's the volume of rotating this, right, around y equals 2. Okay. All right, so what do you want to call that? Were we calling that small volume before? All right, so let's see if we can calculate what the small volume is. All right, so we're going to have an integral here. It's going to involve pi, okay? What are the limits of integration going to be? 0 to what? 1. That's pretty obvious, right? Okay. We're going, again, from 0 to 1 on the x-axis. Nice limits of integration. Don't always expect them to be that nice, but they're nice here, right? Okay. And now, here's the tricky part. Remember, you need a formula for what? the radius of this object, right? Okay, you need a formula for the radius of this object at any value of x. Okay, the radius of this, what's the radius of, not this, but what's the radius of this, right? What's this radius at any point x? All right, so let's just put an x there, because it has to work, this formula has to work for x. All right, so there's x, right? Okay, and so I'm going to draw from x all the way up to y equals 2. That's not the right radius, though, right? Okay, that radius is too big. Okay, what's the piece that I'm interested in? Just this part, right? Okay, I just want that piece, right? So what is this? What is that length? Okay. So how do I get just this length? Well, I think that would be what? This whole length, which is what? 2 minus what? Minus this piece, right? But how long is that piece? 1 minus x. Oh, see, y'all got it there. So nice, right? Okay, right. I take this whole length, which is 2, okay, and then cut off this part, and what's left will be, oh, that's the radius that I want, okay? So you take 2 minus 1 minus x. Remember, this length is 1 minus x, right? Okay. Shall I put that in the picture? So this is 1 minus x. So this part is 2, be careful about the signs here. This is 2 minus 1 minus x, which I guess is what? Is that 1 plus x? Yay. That's the radius. So fill that into your volume formula. But what do you do with it? Square it, right. Oh, great. Okay. That's it. I just have to compute this definite integral. Wow, let's do this. We just have enough time, okay? And then I take the difference here, right? Okay? All right, so let's compute this definite integral. What is the antiderivative? So I'm not going to do this separately. I'm going to do it at the same time here. What is the antiderivative of 1 plus x squared? What can you use? Anti-power rule, right. You can use the anti-power rule. Now, you have to be a little bit careful about using the anti-power rule, right? Because this is not just x squared. This is 1 plus x squared. So remember, you have to make sure, ooh, do I have the derivative of 1 plus x squared multiplied in here, right? I'm essentially doing substitution without doing the substitution, all right? But what is the derivative of 1 plus x squared, of 1 plus x? 1. That's multiplied in here, right? Because you can always put a factor of 1. So you can just immediately use the anti-power rule, right? Okay. So you would get as your, what do you get as your antiderivative then? What now? 1 plus x what? Cubed over what? 3. Evaluated from where to where? 0 to 1, right? Okay. Evaluated from 0 to 1. So I get pi times, this is going to be a little bit uglier than before. When you plug 1 in there, you get, what is that, 2 cubed over 3, so that's 8/3, right? Minus, what do you get when you plug 0 in here? 0 in for x? 1/3, right, okay. So is that 7 pi over 3? Yes, okay. So we end up with 7 pi over 3. That's the inner volume that you're subtracting from the big cylinder, and what's left would be the volume that we were asked for, right? So let's write it down here. What's our, oh, by the way, remember this was what, 4 pi? So our final answer up here is, oh, this volume is going to be the big volume, which was 4 pi, minus the smaller volume, which was the inner volume, which was 7 pi over 3. And what does that work out to be there? Is that 5 pi over 3? Am I doing that right? I think so, right? Okay. So I don't remember that answer. Did I make a mistake there? Okay, all right, so 5 pi over 3. There we go. Cubic something or others, right? Okay, there's the volume. Yay. All right, well, all the problems in the book are like these problems. All right, okay. So in one way or the other, but that doesn't mean that that they're gonna be identical by any means. Okay, so but these examples will certainly get you started. All right, let's stop there because we have to take the makeup. All right, so if you're not taking the makeup, then did everyone sign the roll? If you're not taking the makeup,